Okay, this is Keith Thompson and Jose Garcia here at the Electro-Optical Systems Lab at Georgia Tech, and we're going to give you a little video tour of this wavefront generator. The video hopefully will give you a little better understanding of the device, and you can correlate that to both the drawings as well as the other images that we send you. So we're looking from the top view of the wavefront generator down, and the images or the devices that generate the images, the OLEDs are back here, and they're about 15 to 20 millimeters away from these collimating lens, so the light goes into each of the collimating lens. And you'll see that there's two channels here, one for the left eye and one for the right eye, and they go through the collimating lens, and then they go through this stack of adjustable lenses, this array or stack of lenses. We call those the Alvarez stack, and you'll see in one channel the lenses are present. In the other channel the lenses have been removed, and what you can see down here are the actual actuator wires and the little tongs that clip into the lens holders. So it gives you a good understanding of what those lens holders look like. Then this is where the light exits each of the channel after it's passed through this stack of Alvarez lenses and has had its properties, its wavefront changed by the lenses, and this will go out through some turning optics out to the field mirror that you see in the images and then back to the patient. So we call this box and everything inside this box the wavefront generator. And then if you look over here, I'm going to show you a detail of the lens in a second, but if you look over here on the left side of the wavefront generator, these are actually copper tubes. And in each copper tube you can see that there's either a control rod, which is a 0.5 millimeter diameter cable or rod, or these little wires like you see here. And all of these attach to mechanical actuators. And I think the control rods were simply attached to these push-pull manual slides like this, or we can show you the dials that the control wires were attached to, and those dials would be manually moved. You see there's a yoke, and that motion is transmitted to it through a push-pull mechanism with the wires attached. So that was the actuator assembly or mechanism of this mid-1970s instrument. And of course what we're doing and that we're interested in tasking you with is using this exact box. It's very well engineered, it's very stable, and even after 30 years it still works remarkably well, but we want to automate the motions of these lens holders. And yeah, as we talked on the phone last week, we could either do that using this existing array of control wires and push rods, or if you could come up with some other mechanism to directly attach to these lens holders to make the motions with the precisions that we talked about. Let me next show you in a little more detail how one of these Alvarez lens pairs works. This is a pair of lens elements. They work together to make one change in power. This, for example, I think is a spherical lens. And you can see that when the lens, if you may or may not be able to see this in your video through the lens, you can look at the texture here of this brick. And when the lenses are in alignment, the lens elements are in alignment, there's no optical power. But notice when I start translating the lens elements, you'll start to see the pattern in that brick distorted. And that's because there's optical power being applied that is proportional to the amount of translation of these two lens elements. And again, the control wires would attach through little tongs. Here you see the little holder for the tong, and here's I think I can probably hold up one of these little tongs for you to show you. There's a control tong, and that's actually how it clips into the lens holder, and then it goes in that little tong there, and then this little plate slides over there, and that's how it's held in. And as we talked about before, the 6 of these Alvarez lenses are in a continuous circuit where the wire goes around this assembly of turning pulleys, which I'm going to show you here on the underside of the wavefront generator. And remember, these have no motion at all. They simply reverse the direction of the wire. And again, all the motion was provided mechanically, either with push-pull mechanical rods or the dials. So that's sort of the overview of the generator. You can see how tightly, I'm going to see if I can get the rest of the stack of the lenses that we've removed from this, just to show you how they sit in here. We may be missing
there's two more of it.
A lens somewhere, but basically you get the idea that these things fit together. There's a vertical portion with the holder that holds the lens element, and then there is a horizontal portion which you see rest up against this plate, this forward plate here, and so there's really minimal friction. So the torque needs for the system are very low. You can see just with this one screwdriver, I'm just barely touching this and it's sliding. So there's not a lot of torque with the system.
Frontal lenses right here.
Let's see. Yeah, the lenses that we mentioned, there's 6 of these lenses that are on 3 pair per channel or 6 per side that are on control wires, and then there's 2 forward of those lenses that are on push cables, and you can see those right through here. These lenses have 3 positions. They're out of the way, or they've slid to where one of the 2 lens or one of the 2 apertures is in the beam path. I think you can see that. This one is an orange aperture. This is an accessory lens. So position 1, it's out of the way. Position 2, the orange aperture is in the beam path. Position 3, the accessory lens. So those are the 3 positions that we need with these 2 lens elements that are behind the Alvarez stack, and then there's 2 lens elements that are also on push rods in front of the stack. So again, that's 10 lens elements total per side. The first 2 are push rod. The next 6 are control wire looped around the pulley, and then the last 2 are also push rods. And here, Jose's handed me these. These are the we actually have these labeled. Lens 1, 2, and then 3 through 8 are the Alvarez stack, and 9 and 10 are also push rod lenses. So you can see how they work in that position. Let's see. Oh yes, let's show you the I'm going to turn this around and show you the, as you recall, there were 4 other motions that we needed to talk about that concern these first lenses, which are the collimating lenses. These are the big lenses. They take the image out of the organic light emitting diodes and basically collimate the light so it appears like it's coming from infinity. And you'll see this motion here. These lenses are unlike any of the other different motion. These lenses are yoked so that when you see one on the left side goes down, the other one goes up, and vice versa. And that's accomplished by this little yoke. There's literally a yoke inside of here. You can see it actually very clearly on the drawings. It's a blue horizontal and vertical yoke that rotates around that little pinion down there, and that is controlled by this pulley mechanism here through these 2 control wires. Okay, so that's how that motion is accomplished. These lenses can also slide. They're also coupled so that they can slide together and apart, and again, that's a coupled motion. You see how if I'm pushing the one on the left side, the right side moves in the opposite direction. And that's also accomplished by a pulley mechanism here through these 2 control wires. So that sort of gives you an idea of the motions and what it's like. Hopefully that'll give you a little flavor of the device, and I'll give you a little close-up here of where all those control cables. These here, these first 4 are the input cables that control the collimator lens that we just showed. And then we have a total of 10 pair of control wires or cables that go in through this side port here. And for the purposes of your task and automation, this could simply be severed here to give you direct access to the control wires if you wanted to use the same configuration that this original device came in. And let's see what else we've got here. Underside of the device, nothing really very tricky there.
There's actually a cover.
Plate. There's a plate. That's right.
Covers on the bottom and a cover on
the
top.
top to keep dust from getting in the optics. This is pretty much standard base aluminum. According to Dave Roberts, who's an experienced optical guy, this is very commonly used in optical mounts and so forth. So no elaborate machines. One other final thing to mention, because we talked about the need to have a coding, decoding technology to tell us where these lenses are, and there's a couple places that you might think about adding that. You notice this lens plate rests up against both the front wall here and the back wall here, and we need to know, or would like to know, exactly where that lens element is in its translation motion, as well as all of the lens elements for that matter, but especially its pair, because the relationship would then tell us exactly the optical power that the lens elements are providing based on their translational positions. So it might be possible to put either an optical or a capacitance-based coder, decoder, either on this wall or the other wall,
or in between.
Something that you guys might consider. So that's an overview of the system, and let's see if we've got any other angles here to show you. This is the plate that mounts the turning pulleys that you see here. Each one of these is a pair of pulleys, and all of these wrap this very thin wire. I believe it's 0.2 or it's 0.05 millimeter.
And they're double. So
thickness,
2 wires go through them.
2 wires for each of these pulley sets.
And these first 2 are only guides.
Right. And there's a very detailed picture of this on one of those drawings that we sent you previously. So hopefully that'll be helpful to you in working up your proposal, and we look forward to hearing from you guys. Give us a call if you have any further questions.